Let us see thiophene. Thiophene is a heterocyclic compound with a formula C4H4S. Consisting of a planar 5-membered ring, it is aromatic as indicated by its extrinsic substitution reaction. It is a colorless liquid with a benzene-like border. In most of its reaction, it resembles benzene. Compounds analogous to thiophene include furane, selenophene and pyrrole, which each vary by the heteroatom in the ring. Preferred IUPAC name of thiophene and other name is thiofuran, thioacylopentadiene and then thiol. Isolation and occurrence of thiophene. Thiophene was discovered as a contaminant in benzene. It was first observed that isatine forms a blue dye if it is mixed with sulfuric acid and crude benzene. The formation of the blue indophenin had long been believed to be a reaction of benzene itself. Victor Meyer was able to isolate thiophene as the actual substance responsible for this reaction. Second one, it is prepared from petroleum compounds. Sometimes in concentrations up to 1 to 3%, the thiophenic content of oil and coal is removed via the hydrodesulfuration process. In hydrodesulfuration process, that is HDS, the liquid or gaseous feed is passed over a form of molybdenum disulfide catalyst under a pressure of hydrogen. Thiophenes undergo hydrogenalysis to form hydrocarbons and hydrogen sulfide. Thus, thiophene itself is converted to butane and hydrogen sulfide. More relevant and more problematic in petroleum are benzothiophene and dibenzothiophene compounds. Synthesis and production of thiophene. Reflecting their high stabilities, thiophenes arises from many reactions involving sulfur sources and hydrocarbons, especially unsaturated ones. The first synthesis of thiophene by Meyer reported the same year that he made his discovery. Thiophenes are classically prepared by the reaction of 1,4 diketones, diester or dicarboxylate with sulfidizing agents such as P4 esters, such as in the form of Paul-Nor thiophene synthesis. And then thiophene is produced on a modest scale of around 2,000 metric tons per year worldwide. Production involves the vapor phase reaction of a sulfur source, typically carbon disulfide, and a C4 source, typically butanol. These reagents are contacted with an oxide catalyst at 500 to 550 degrees Celsius. At room temperature, thiophene is a colorless liquid and it is the odor similar to benzene, with which thiophene shares some similarities. The high reactivity of thiophene toward sulfonation is the basis for the separation of thiophene from benzene, which are difficult to separate by distillation due to their similar boiling points. Like benzene, thiophene forms an azeotrope with ethanol. The molecule is flat-like structure. The bond angle at the sulfur is around 93 degree. The carbon-carbon sulfur angle is around 109 degree, and the other two carbon have a bond angle length 114. The carbon-carbon bonds to the carbons adjacent to the sulfur about 1.34 Armstrong degree, and then carbon sulfide bond length is around 1.70, and the other carbon-carbon is about 1.41 Armstrong degree. The reactivity of thiophene is aromatic, although theoretical calculations suggest that the degree of aromaticity is less than that of benzene. The electron pair on sulfur are significantly delocalized in the pi electron system. As a consequence of its aromaticity, thiophene does not exhibit the properties seen for conventional thioethers. Oxidation can occur both at sulfur giving thiophene as oxide, sulfur oxide, as well as at the 2,3 double bond giving the thiophene 2,3 epoxide, followed by subsequent NiH shift rearrangement. Oxidation of thiophene to form dry fluoroperoxytic acid, and then Diels-Alder type of dimerization and further oxidation forming a mixture of sulfoxide and sulfone products. In the minor reaction pathway, a Brill-Serve epoxidation results in the formation of thiophene 2,3 epoxide that rapidly rearranges to the isomer thiophene 2-one. Oxidation of thiophenes may be relevant to the metabolic activation of various thiophene containing drugs such as thymic acid and the investigational anti-cancer drug. Alkylation reaction. The sulfur atom is relatively unreactive. The flanking carbon centers, the second and fifth position, are highly susceptible to attack by electrophiles. Halogens give initially 2 halo derivatives followed by 2,5 dihalothiophenes. Chloromethylation and chloroethylation occur readily at the same 2,5 position. Reduction of the chloromethyl product gives 2-methylthiophene. Hydrolysis followed by dehydration of the chloroethyl species gives 2-vinylthiophene. And then polymerization reaction, it undergoes polymerization reaction to form 2,5 position polythiophene. And then polythiophene itself has poor processing properties, and so it is little studied. More useful are polymers derived from thiophene substituted at the third and fourth position, such as ethylene dioxythiophene. Polythiophenes become electrically conductive upon partial oxidation. Therefore, they obtain some of the characteristics typically observed in metals. And then uses of thiophene. Thiophenes are important heterocyclic compounds that are widely used as building blocks in many agrochemicals and pharmaceuticals. The benzene ring of a biologically active compound may often be replaced by a thiophene without loss of activity. Thank you.